Третий курс. Молодцы. Сегодня вопросы будете задавать? Ну, по-русски. Так, окей. Сегодня у нас вторая лекция этого же цикла. Большинство было на первой лекции, так что введение можно не делать. Ну и это продолжение, в общем-то, этого направления исследований. Okay.
Okay, so thank you for your introduction. So this time I will show you how droplets can move and move as, in fact, they behave the same way as if it were a micro steam engine. You know the steam engine, the locomotive, that's adiabatic. But when you reduce the size, you cannot have any more adiabatic steam engine because the heat diffusion is very fast. So you can have only isothermal steam engine. And to make isothermal, you have to account for the latent heat of condensation. And that's why what I will show you, it's a kind of micro steam engine. So, it doesn't work?
No, it should.
On.
It should.
Okay. No, it's okay. So this is a work I started a long time ago, but the recent development are with Ramchandra Ranare. He is now a professor at Pune University in India. He's from India. Pune is a big city near Mumbai. That's a very big city. Very dirty. And so Sushantanan is also from India, and Kripavarasi group, and these are from the MIT group, and Konrad Rikazewski is from the NEST, the National Institute of Science and Technology in Washington. So this is the experimental setup that is in my lab. So that's basically a microscope. You can see here. You have a condensation chamber. It's made with a copper and a plexiglass. Here we have a Peltier element behind a copper disc. So we cannot see very well with the light. And this copper block is cooled by a Peltier element. And the hot side of the Peltier element is connected to water bath, so constant temperature. That will change the temperature to around, we will see, around 3 Celsius. So that's the cooling of the Peltier, as I told you. And there is a airflow inside, which is at room temperature and 100% humidity. So we provide 1% humidity by bubbling air into water. So the bubble takes the moisture, and after it is 100%. And there are thermocouples at the surface of the copper that to measure the surface of on which we will put the sample. So now we have also a fast camera above it, or a regular camera, which is connected to a computer. Now that's a picture. So you see, just to tell you, so that's dry nitrogen or air with a fish tank pump is bubbling into this Erlenmeyer bottle, and so it's making a lot of bubbles, and after the humid air is coming this way. So that's there is an inverter. It means that you can also send dry air by sending air into a desiccator. So that's good to. So basically, the experiment is to send dry air, so you have no condensation. After you open the humid air instead of the dry air, so condensation starts. So we know exactly the time where condensation starts. So that's another experiment, which is. So we have the same Peltier, the sample, and we look from the side. Now, what we will look, that's the condensation of water on cyclohexane or benzene. And the melting point of cyclohexane is 6.5 Celsius, and benzene is 5.5. In fact, we'll see later that there are many other materials whose melting point is around the same or below. But what I will show you don't work, because when you freeze these materials, they crystallize. And so when the water droplets condense, they are pinned to the crystals and they cannot move. Here, and that's something we have to understand, we will study further, because that's only with this C6H12, C6H6 materials. When you cool them, when they freeze, they seem to make a very soft surface, a kind of glass. I think they solidify as glasses. Now the condition of the supporting device, that's 3.4 Celsius, so that's below the melting point. So these are solids, but you condense. Air temperature 24 degrees, humidity 100%, air flux, well, that's on the other 0.2 liter per meter, or also we can condense directly from the atmosphere, from the moon. So there were two important papers that we, in our group, we did. The first was the discovery of this condensation and the motion of droplets. In fact, to tell the truth, I observed by chance this motion earlier, and this was my student, so I asked him to, during his thesis, to see all the parameters. And that's more recent, and this is on benzene. Ram Chavanara did the work in India. Okay, so now I will show you the movie, and the first movie. Here it is. So during condensation, you see the droplets, they're condensed and they are really moving. They are moving very fast. So by changing the conditions, so again, so that's real time. By changing the condition, you can tune the velocity and see better what's going on. You see that, so this is much slower, and you see what they are doing, the drop, they are moving rapidly from one position to the other. They are staying sometimes, growing, and after, well, we say jumping. We see that they don't really jump. So, if you look carefully, you see that there is something left behind, and also they leave a trace, and the trace is smaller than their diameter. It means that, in fact, when they jump, they spread, and after they reconcentrate. You see? This is larger than the perimeter left on the support. So it seems that the drops, they grow gently, and suddenly they spread, and when they spread, they move. And after, the diameter diminishes. By condensation, there is a slow growth, and they move. Now, we can look, this is on cyclohexane. We can look with a fast, of course, that's with the fast camera. So can you see it? So the motion is accelerated by 1,000. That is. So I think it should again. You see. So that each frame here, you see, there is motion like this. Each frame is 250 milliseconds. And you see that when that's pinned, and when they will move, the diameter will increase. Okay. So that's something. So that's something you have to keep in mind to understand. Now, So that's on benzene. So that's interesting to see that they are big crystals, but very, very soft at the beginning. You see at the beginning, these are crystal of benzene, but that's soft. And you have condensation, that's very tiny droplets. Okay. They look like beetles, and they move, you see, but the same kind of motion. So they stay, and they jump. And after the size diminishes, they spread, they jump, etc. See, and they leave something on the surface. They are bigger. Of course, when two drops touch, they coalesce. They coalesce, but they don't coalesce onwards. Okay. So you see, definitely there is a transformation from heat to motion. That's an engine. Now, if you have some idea to get the motion, I will buy it. Okay, so I go a little bit further. Now, you see, if you look from the side, you see that that's cyclohexane, that's water, and you see there is something here. That is, there is a layer of melted cyclohexane that imperfectly wets water. So this is solid cyclohexane. Well, we don't see. Maybe we can. No, it's not possible to reduce the light. We have a photo of it. Yeah. Because on the picture you could see something around the drops. In the movies you could see around the drops this kind of neck. So that's liquid cyclohexane, and so we can measure with a tangent the angle between the surface of liquid cyclohexane with air and the surface of the water with air. That's θ3. Now, if you look from above, you see that there is a ring left, and the ring corresponded to the previous perimeter of the drops, and you see that once the drop has jumped, its diameter is definitely larger than the print on the surface. And also, it's not very, here also you can have some, you can see this kind of wetted layer of cyclohexane, but depending where you focus, you see it or not. So now that's another picture, and you see definitely the layer of wetted cyclohexane around. Now you see that the motion is different. If you look at the details, you can see many jumps, and you see that there is something left on the surface. Now the question you can ask, and okay, that's interesting also, it happens that two drops touch, but since there is a layer of melted cyclohexane, you see, they don't coalesce immediately, because here you can see the two drops here, like this. They didn't melt, and there is a layer of melted cyclohexane between them, and it takes some time to remove this lubrication film. So it takes some time. Now the question we ask is, the liquid or solid print ridge, is it an upward deformation, that is a ridge, or is it a trench, that is a downward deformation? From optics, you cannot tell. You cannot tell whether the print is something like this or something like that. So for that, in order to test, we use a technique which is a cryo FIB SEM, that is cryogenics focused on beam milling, scanning electron microscope. So we freeze very rapidly the pattern into liquid nitrogen at 90 K, and after we look at the electron microscope scanning, and we can make a cut with by focusing ion beam. So milling, it is removing. So that's the picture you can get from SEM, and you see that's interesting because the print definitely corresponds to something above and not below. Also, you see there is some detachment of water droplets, and this detachment is due to the fact that when you freeze, the thermal expansion of the water is different from cyclohexane, so this can detach. But that's interesting because you can see the shape, and this corresponds to the liquid cyclohexane around the droplets. So that's another view. And so from this picture, you can get the contact angle between water and liquid cyclohexane, which is theta s. So now if you mill the drops, this kind of drop, for instance, you mill it, or this one, you get this picture. So this is water, this is solid cyclohexane, and this was the liquid cyclohexane that has been frozen, and this is solid cyclohexane. And so we can measure this contact angle theta 3, and hopefully that's the same as the one which is here. I don't give you the number, but that's about 150 degrees. And this corresponds to the surface tension. So from surface tension, you get the same number. Here you get the contact angle from water, liquid cyclohexane. Here, so you can get all these numbers. Now something interesting, that's this contact angle with solid cyclohexane. In fact, that's more complicated because you see that here you have the solid and here you have the liquid. So it means that here you have liquid and solid cyclohexane in contact. So that's a non-equilibrium situation. And you see that this contact angle is very high, which corresponds really to a non-equilibrium situation. You have solid cyclohexane here, liquid cyclohexane there, and you understand that this corresponds to the fact that the temperature of the substrate near the water and at the liquid cyclohexane and at the water, that's about the melting temperature. So there is a gradient of temperature between the solid here and the liquid cyclohexane and water. So here solid cyclohexane is slightly below the melting temperature and water is slightly above. It is above because here you have a liquid. So you know the thermal properties is important for this problem. So now that's interesting because you see this was a drop that has jumped and this was the print. You can see the print here. It has jumped over there. Okay, now in order to understand this motion, I have to tell you a little thing about the growth of droplets. For those people, for you who were on Monday at my talk, so you know everything, so please excuse me. But you know that if you have one single drop, and that's the case here, you know, the drops, they are rather isolated. They are not so close together. Some are close, some other are not. So you have well away from the drops, you have a constant concentration of water molecule, which correspond to the vapor pressure at this temperature and this humidity. And now at the surface, you have a temperature which is the substrate temperature, and you have the saturation pressure at that temperature, which corresponds to the concentration of water molecules. And now, of course, by Brownian motion, you have the water molecules into here that are in a Brownian motion. When they hit the drops, they are incorporated. This means that the probability for molecules here to be incorporated is larger than there, so the concentration of water molecules is less than here. So a concentration gradient naturally forms by Brownian diffusion of water molecules. So in order to determine the concentration profile, you have to solve the equation. The evolution of the number of molecules for the concentration is due to the fact that these appear by diffusion in the gradient. So, and the volume evolution of the drops is simply the integral of the flux of the water molecules diffusing towards the drop at the surface of the drops. And this current, can be expressed as the gradient of the concentration at the surface of the drops by the diffusion constant of the drops. So in order to get this volume evolution, you need to know dN over dr at the surface of the drop. So you have to solve this equation and get n over r. So you need the concentration profile. So for that, so as I told you on Monday, to solve this equation is very difficult because that's a moving boundary problems. And so it can be solved analytically only for a few conditions. This, for example, two-dimensional with constant flux at the border. So you get a log profile. But if you assume that during the growth of the drop, the profile doesn't change very much, so you have a much simpler equation, which is the Laplacian of n equal to 0. And so in hemispherical geometry, you get hyperbolic profile. You see that with the boundary condition that when small r is equal to the radius of the drop, you get saturation, ns, and when you go to infinite, you get n infinite. So when r to infinite, you have infinite, and the 1, you get ns. Now, to get the volume evolution here, you get dV over dt, so you express dV over dt this way, that's, you assume it is hemispherical, and you get the sum of you get the dN over dr over the drop, so that's this derivative, and you express d12, and you express the surface, so you integrate on the surface, so you have something proportional to r. Of course, there are some 2 pi over 3, etc., but I remove all these geometrical factors. And so you see that you get immediately, when you integrate this equation, you get r, which is proportional to the time, to the root square of time, the square root. And so, with a prefactor that depends on the supersaturation. Okay, so I won't go further, that's enough. Now, the interpretation of the motion is the following, but you can discuss, perhaps there is another one. First, you have the substrate, and if you look at the substrate when there is no water drops, you can, the temperature of the surface here is determined by the balance of the flux between heating from air, so that's a boundary layer, air boundary layer, and cooling from the Peltier through the materials, each at the thickness of the materials. And of course, Tc is determined, the temperature, by the fact that both flux are equal. So this determines the condensation surface temperature. Now, as I told you, the drops here, when it condenses, here nearly at the melting temperature of cyclohexane. So, when it condenses here, there is, in addition to this balance, there is condensation latent heat that is given to the drops. And so this means that the temperature of the drop increases and increases towards Tm. And when it reaches Tm, it can melt the layer below. And what happens when it is melted? The drops contact angle, the drop is not pinned anymore, and so it spreads and moves. So that's first to understand this motion. We can calculate the melting time versus the radius. That is, you know, the drops they don't move for a time, and after they move. So the melting time, that's the time during which the drops is immobile, doesn't move. That's this time Tm. And with respect to the radius, it's proportional to the radius with a slope alpha. Okay, now we can try to express this time Tm. And in order to prove it is really proportional to R. That's simple and not simple. You know, we just have to express that we melt the layer beneath the drops of thickness E. So of volume pi r squared, r that the radius of the perimeter here, multiplied by E. So we have to express the balance. So we have on one side you have heating by air, so that power during the time Tn, and you have the latent heat of water during that time. Now this heat corresponds to the cooling power of the Peltier, plus the fact that you have to heat the layer, so that's the sensitive heat of cyclohexane, of solid cyclohexane, and you have to melt cyclohexane, so that's the latent heat. Okay? So you have to express this. At the very beginning, we know that the power from air and the cooling power is the same. And after we have to express how the latent heat is brought to the substrate. So you have this power corresponding to the volume increase with the latent heat. And so this can be expressed from the growth of the drop. That's a geometrical factor. And that's the volume increase. And so you get something which is proportional to k squared r, proportional to r, according to this growth law. R is proportional to time, r is equal to kt, and so you get this equation simply, that is dV over dt is proportional to the radius from this growth. And now the third thing, you have to express the sensitive heat to bring the substrate temperature from Tc to Tm. So that's the volume of the layer, the density, the specific heat of solid cyclohexane, and the difference in temperature between Tm and Tc. And third, you have to express the latent heat, the energy, to melt this layer, which is proportional to the density of cyclohexane, the volume R2, and the latent heat of cyclohexane. So we have everything. Oh, that's simple calculation. That's for students. So, but it has to. This will be a nice examination. That's. Yeah. And so when you solve this equation here, you get Tm, which is proportional, indeed proportional to R, with this prefactor where you see the latent heat of cyclohexane. Okay, I forget there is a ratio of cyclohexane and water density, latent heat of cyclohexane, specific heat, but this is usually small. So you see that's nice because you have the ratio of density and the ratio of latent heat. Of course, the latent heat of water is much larger than the latent heat of cyclohexane. It's much larger. It's larger. That's a factor of 2 to 5, I think, not too much. And that's because the latent heat of water is mainly used to melt to heat and melt the layer. So that this is a formula that you could write by hand because it's really logical. So h of theta, that's only a prefactor like 2 pi divided by 3. K squared, that's the growth rate of the water droplets, and E, that's the thickness. Okay, so now, second stage, once the layer has melted, you see, there is no spinning anymore, so the drops, when the drop grows, it is pinned, so the contact angle goes to the advancing contact angle. When it is not pinned, up, it spreads. It spreads, and there is some always, so it means that there is a capillary force, and the balance of the capillary force around the perimeter is not zero because the perimeter is not strictly circular. So there is always a force that will move the drops to some random direction. Okay, here it is. So melting, sliding, and if you if by measuring alpha and k, all this is known, you can determine the thickness E. And if you make the calculation, the thickness E is very small. That's about 200 nanometers. So this means that once the drop has left the cold substrate and is in contact with the cold substrate, it immediately freezes. That's why the motion of droplets you have seen is always on the perimeter. It cannot go further because it immediately freezes. And so now the motion can be interpreted this way. That is, it is spin, and suddenly, it's like you were on spring, suddenly you cut the ropes, and so you go to the other place. Okay? So remember the movie. So that's the initial size of the drops, and it moves immediately once it has spread, what it has depinned, in fact. And so we can measure the motion. That's, rather random motion. It's on a layer of liquid, so depending on the details of the substrate, you go right or left. So now we can measure the distance, the distance traveled by the drop versus time. Here it is. So if you look at the distance traveled by the drop versus time, you see that it grows linearly in time and suddenly stops. That's because it freezes, the layer freezes. And you can determine the distance traveled during the time traveled, and so this gives the velocity, and you see the velocity is constant. So here that's the time to travel is proportional to the radius. And of course, since the velocity is constant, the distance also is proportional to the radius, and you see that it's always proportional to the radius with a slope with a prefactor that's on the order of 1, that's 1.5. And that's nearly the same value on cyclohexane and benzene, that is on the order of 1.5. And I told you because once it has moved, once the drop has gone from the place where it was at the melting temperature, it is on a colder temperature and the layer is so thin that it freezes immediately. Now we can express the capillary force. The capillary force, that's intervention tension by the radius, and by the difference of cos theta between the spreading, between the advancing and on the liquid. So that's on the order 1. And this is compensated by the viscous forces, that is the shear viscosity, and the velocity of the drops and the radius, the perimeter of the drops. And so it means that the velocity is a constant, is proportional to sigma divided by eta. That's something which is, that's a capillary number. And it can be measured by the Sg divided by Tg, that's this value. There is a prefactor B, but you know, Tg, that's on the order of 2 microseconds for 180 nanometer. So, and that's much smaller. This means that B is on the order of 10 minus 3. But that's normal. So now, if you look at the capillary force, you can there is also some oscillation of the drop. You can calculate the drop oscillation, and that's typically for a drop of 78 microns, as these drops here, it's 0.1 millisecond. So now if you see how the radius from this, you can measure the radius with time. Of course, at the beginning, there is a big change of radius, because you see it spreads, and after there are some oscillation, but you see, we expect oscillation of 0.1 milliseconds, but our resolution is 0.25 milliseconds. So we can see only a weak oscillation. But after, say, if few oscillation, the drops doesn't move anymore. Anyway, it is frozen. So you see that during the motion, which lasts about 4 milliseconds, at the beginning we have oscillation, and after it is stable. So you understand what's going on. So the drops is on the surface, latencies of water is the surface, and suddenly it melts the substrate. So the drops move, and at the same time there are some oscillation, and it stops when the drops has been away from the initial position. Now the third stage, once the drop has stopped, so it is rather spread like this, it's freeze this way, but it has to recover its contact angle at equilibrium on solid cyclohexane. So it has to contract. And so the contact line has to move. And this is something we have studied by the coalescence of two drops, and that's a very slow process. It's a slow process because you have to depim the contact line, and you have to make, that's an interesting problem, because when the contact line moves here, the velocity, the contact line moves, the velocity, let's imagine it moves, the velocity at the contact line at the substrate should be 0, because it is 0 on the surface. But if it is 0, the contact line doesn't move. So there is a paradox. And this paradox can be solved by telling that the motion of the contact line is due to a phase transition. That is, you have molecules, you have evaporation, condensation, evaporation, condensation. And we know that this process is a slow process. That's why. So now for the relaxation, so we go from this position to that position, and that's a very slow process. That's an exponential, so the radius is decreasing with time. So you see now that's not millisecond, but that's 1,000 on milliseconds. That's 3 seconds. That's very large. And if you look at this typical time versus the radius, okay, so, sorry. Okay, you see that's proportional to time, and in fact this corresponds to a velocity, in fact, but with a prefactor k, which is on the other 1 or 10 millions. It means that the viscous dissipation, if we add only viscous dissipation to recover the shape of the drop, we'll have a time which will be eta over sigma by r. But the fact that there is a contact line makes a prefactor which is on the order of 1 million, 1 or 10 million. And that's due to the fact that the contact line has to move. So the problem, you know, if you have a bubble, droplets in zero gravity, and you deform it, and so it will recover its initial shape by after some oscillation. The velocity, the time to recover it, will correspond to this velocity, so it will be this typical time with k is equal to 1. But now if you put this drop on a surface with a contact line, the time to recover its initial shape is multiplied by 1 or 10 millions. That's due to the fact that you have to move the contact line. So the physics is different. The contact line, you have a microscopic scale, and you have strong effect. Okay, so now there is another motion which we call the crawling motion. It is sometimes the drop, you know, here you have the drop, they stay and they jump. I will say they stay and they slide, they stay and they slide. But there are some other motion which are nearly straight. I will show you that's a movie. So there you see that's two drops. Now they merge, and now they are making not jumping motion but straight motion. And here also you have, see. Okay, so the interpretation, I don't go into much details, but you know, to have the what I call the jumping motion, it means that when the drops moved, when it has been ejected from its initial perimeter, the layer beneath freezes immediately. If, for some reasons, like for instance, when two drops merge, this layer is thicker, it doesn't freeze. And so the drops can move continuously, and there is always small gradient, and if there is a gradient, it means the drop will move due to the kind of Marangoni effect. That's what's going on here, you see. But after some time, this layer thinners, and you always recover the hopping motion. Look this. Now that's hopping motion. Okay, so I have finished this presentation. Now the question is this motion general? So we tried, at the MIT they tried also to look for many other substances. It's not working on the other because, as I told you, they solidify with crystals, and the crystals that are like spines. So the drop form on the spines, but they are really stuck, so they cannot move this way. So you need a rather smooth surface. Now, as I told you also, this is an interesting example of steam engine. You have hot and cold sources, hot surfaces that's air, and cold that's the condensing surface. But the process is isothermal in the sense that that's due to the release of latent heat that the motion is produced. I think that's an interesting point. I've seen only one paper discussing this micro steam engine, how to make a micro steam engine when you are reducing the size. By Japanese, it was about 10 years ago. But nobody has studied further this question. I think that's an interesting question. Okay, so I thank you very much for your patience. If you have some questions.
Thank you very much. Вопросы, пожалуйста.
I have to tell you that's an easy experiment to do. So if you are interested in studying this process, this would be quite easy.
Many of them are experimentalists.
Yeah, so you could try. That's really impressive.
Так что вы можете попробовать.
But don't use benzene. That's carcinogenic, you know. Cyclohexane is okay.
Циклоэксан есть у вас? Есть, наверное. Он часто используется. Ну что, есть вопросы? Есть вопросы? Люда не знает. Денис, у вас нет. Ну тогда поблагодарим докладчика за очень интересное, я считаю,